I'm from the United States Naval Academy, but I come in peace. One of those comments by James Oxley was directed at me for working for the Navy. There's a bunch of civilians that work in the math department. We haven't yet figured out how to weaponize matroids, but I'm going to talk about delta-matroids as subsystems of sequences of Higgs lifts. So there's a bunch of words in there that may sound like you don't want to hear about them. But I'm hoping that you remember everything that Steve said from his talk yesterday. And so delta-matroids should be friendly towards you right now. And everybody's staying in the Delta Hotel, because matroid theory lives in delta-matroid theory, in a way. At the last of these talks, last of these conferences, I talked about how delta-matroids have something for everyone. They sneak in unexpected ways. You may find yourself studying delta-matroid theory without realizing it. If you're interested in embedded graphs, or partial duality, circle graphs, symmetric or skew-symmetric matrices, or it pops up in DNA recombination in ciliates, then you're going to be interested in delta-matroid theory. And there's more things to add to this list that I'll tell you about. Oh, and on the first slide, I listed a bunch of co-authors, which has become the norm for presenting delta-matroid theory talks. I'm primarily presenting results with Steve Noble and Joe Bonin today. So delta-matroids, you saw a slide just like this, I think, yesterday. You can not. I have what looks like the basis exchange axiom written in a kind of wonky way up there. So this looks like the basis exchange axiom for matroids, except instead of taking an element out of B1 and taking an element from B2 and sticking it in to replace it, I'm using symmetric difference. So I'm not saying where the elements come from. They're in the symmetric difference, but they're not necessarily in F1 or F2. So I've got my delta-matroid D, I've got my ground set E, and my set of feasible sets, which are all subsets of the ground set. The symmetric exchange axiom holds. And as long as you don't have the feasible sets being empty, you have a delta-matroid defined by André Boucher. So the only difference between matroids and delta-matroids is one little axiom that I left off this slide. So what's the missing, what's number 3? What is it, James?
Equicardinality.
Equicardinality, to say it in the Australian way. Equicardinality. So for delta-matroids, I don't have to have my feasible sets being equicardinal. As a matroid theorist, you may think, well, that's kind of wonky. But the feasible sets of my delta-matroid are going to behave the way bases behave in matroids. And you get some matroids out of a delta-matroid. When I think about delta-matroids, I like to think about my feasible sets in a kind of stack. So I put all the smallest ones in the bottom level, and the next size up, I put them in the next level, and so on. So I put all the smallest ones in the bottom level, and if I just focus on those, it turns out that the symmetric exchange axiom holds for those as well. So I have symmetric exchange axiom holds, they're equicardinal, so that's a matroid, which we call D-min. The top layer is also a matroid. So that's really nice. If you like matroids, you should really like delta-matroids. The intermediate levels, you've got no guarantee. It's not necessarily going to be a matroid. So that's D-min and D-max. I have to tell you something about quotients. I use Q to be the quotient and L to be the lift. These are two matroids defined on the same ground set E. And Q is going to be a quotient of L, and L is going to be a lift of Q. Exactly when there's some third matroid where deleting X gives you L and contracting X gives you Q. So the rank of Q is bounded above by the rank of L. And this might sound like a truncation, like you might think, oh, that sounds like a truncation operation that you're doing. Well, in the case that M is a single free element extension of L, it is a truncation, but in general, you're not going to have that. So that's a matroid quotient. And now I'm going to give you a lemma about matroid quotients. The following are equivalent. When I have Q being a quotient of L, then L dual is also a quotient of Q dual. Each circuit in L is a union of circuits of Q. So when you have something being dependent in L, it's going to be dependent in Q. And you can see something happening with rank difference. So if I look at a set in Q and a set in L, and then I add an element to each of these sets, the amount that the rank goes up in Q is bounded above by the amount that the rank goes up in L. So if I add an element E to X and the rank goes up in Q, the rank has to go up in L. It goes up by 1. And if it doesn't go up in L, then it can't go up in Q. Quotients are really naturally related to each other. And you can think about taking two quotients, or sorry, one quotient and its lift, and you could think about filling in all the missing quotients by lifting from Q towards L. So if I lift from Q towards L, whatever the rank difference is, I'm going to say that's K. I'm going to lift from Q towards L to get one rank higher matroid, and then from there I'm going to lift towards L to get 2 elements higher in rank. And each intermediate guy is going to be a quotient of the top guy and have as a quotient the bottom guy. And that's a nice way to get a stack of matroids. And it seems like, oh, well, now I have bases of these matroids, and all these bases have different sizes. What's going on there? Maybe it's a delta-matroid. So what I'm doing, I have to tell you, I'm doing the freest possible quotient of L that has Q as a quotient and has the right rank at each layer. So that's formally what H sup I sub QL is. And if I look at just the bases of one of those intermediate guys, I get all the sets that have the right size. So it's got the rank of Q plus I, that's its size. And it's going to, in Q, it's going to be spanning, has to contain a basis, it has to be spanning in Q, and it has to be independent in L. And that will give me all the bases of one of those intermediate guys. When I take the union of all those sets of bases, I get the set of all sets that contain a basis in the bottom guy, Q, and are contained in some basis of L. Boucher showed, I covered up the microphone. Boucher showed that D min is a quotient of D max. So we could put D min at the bottom and D max at the top and fill in all of these Higgs lifts. So the Higgs lifts between the two matroids. And this gives us a structure in which a delta-matroid could live. Actually, it is itself a delta-matroid. We like to think about graphs as sitting inside of complete graphs. We like to think about representable matroids as sitting inside of projective geometries. Well, every delta-matroid sits inside of this set of Higgs lifts. And we say that my delta-matroid is a Higgs lift delta-matroid exactly when equality holds. So if you have all of these sets that you could possibly have being feasible sets in your delta-matroid, then you have a Higgs lift delta-matroid. For example, if we have the empty set being feasible, and we have a set AB being feasible, and it's a Higgs delta-matroid, then what other, has anybody been paying super close attention? They can say any other sets that will be in that delta-matroid. So the delta-matroid, the Higgs delta-matroid, it's every set that contains a feasible set in the bottom matroid, so it should contain the empty set, and is contained inside of a basis of the top matroid. The top matroid here is just got one basis, that's AB. So, yeah, so it's got everything. So it's got to have everything. Steve talked about minors. Is that correct? Yeah. So minors behave exactly as they do in matroids. When you delete an element, you remove all the bases that contain it. In this case, you remove all the feasible sets that contain it. Contraction, you remove all the things that avoid it. And then from your remaining feasible sets, you remove your element from each of them. And that's contraction. It doesn't work out if you have a loop or a co-loop. In that case, you set the deletion and the contraction equal to each other, and you get your minors all well defined. And every minor of a delta-matroid is a delta-matroid. So these are two delta-matroids. You can check that the symmetric exchange axiom holds. But neither of them is a Higgs lift delta-matroid. So the word theorem probably it's not the right word here, but this is some small thing to notice, that a delta-matroid is a Higgs lift delta-matroid, meaning it comes from this sequence of lifts, if and only if it has neither of these as a minor. So you can characterize these with excluded minors, which is everyone's favorite thing to do. I talk a lot about excluded minors, but I'm not anti-minor. Currently growing a minor, so lattice paths are a really nice set of lattice path matroids are a really nice set of matroids. You can get a matroid by looking at a lattice path and naming your steps as you go. You can say, this is my first step. I'm going to go north, and then I'm going to go east. Second step, 2, 3, 4, and you count your steps as you go. Here I've only labeled, on paths that start from S and go to T, I've only labeled the north steps. So if you go east first, I didn't label it. But then you can go north for step number 2 and north for step number 3. And if you just think about the north steps that you take as you walk from S to T, you'll get a collection of bases of a matroid. And that's called a lattice path matroid. So for example, the set 1, 2, 5, 8. That would be north, north, east, east, north, east, east, north, east. That will give you a basis in your matroid. And these are a really nice class of matroids. You can characterize them with excluded minors, and Joe Bonin can tell you all about that. But if I take S and T and I stretch them out, now when I'm starting at SQ and I go to T0, I'm only going to take one north step. When I start at S0 and I go up to T4, I'm going to take many more north steps. So now if I stretch out S and T, I get paths that have a variety of different numbers of north steps. And what I'm going to get is actually a delta-matroid. And you can see D-min and D-max living inside of there. So from SQ to TP, where SQ is S3 and TP is T0, that's where I get my D-min. And can you see how it kind of sits in there? And the taller one, that's D-max. You've got a lot of north steps. So this is the grid for D above the lattices for its lattice path matroids D-min and D-max. And every lattice path delta-matroid is a Higgs lift delta-matroid. You get all the intermediate sets that you can. Unfortunately, it doesn't hold in reverse. You can't just take any pair of lattice path matroids where one is a quotient of the other and say, well, this is going to be my D-min and this is my D-max, and I'll get a lattice path delta-matroid. It doesn't work like that. This is an example of a pair of lattice path matroids where one is a quotient of the other, and you cannot get a delta-matroid that has those as D-min and D-max. So just in case you were hopeful in that direction. And the last thing I'm going to talk about is an excluded minor characterization for delta-matroids. So every ground set together with a feasible set of feasible sets gives you a set system. If you have the symmetric exchange axiom holding, then you have a delta-matroid. But minors work the same in set systems. You have to use a little bit of care. But minors, you can think of minors working the same in set systems as they do in delta-matroids. So if I look at a set system that is not a delta-matroid, for example, I could take the empty set and then just a 3-element set, ABC, and the symmetric exchange axiom can't hold when I take that as being F1 and F2, because there's nothing a distance 2 away from either of those sets. But if I take the deletion of any element, what's left is just the empty set, which is the basis of a matroid and the feasible sets of a delta-matroid. And if I take away, if I contract any element, I'm just left with a 2-element feasible set. So this is an excluded minor for the collection of delta-matroids. It's a set system that's an excluded minor. That's going to hold if I take any set system where I have just the empty set and the full set, and the full set has at least 3 elements. So you can get an infinite family, and maybe you would hope, oh, if we're doing an excluded minor characterization, we don't really want infinite families. We like it when we can find the names of all of them. Well, these are nicely structured delta-matroids, so I kind of think this is an okay infinite family. But we take all of the set systems that fall into that description, and we have to take all the partial duals of all of those guys, which I'm not going to tell you what they are. Steve, did you talk about this? Yeah, everybody knows. These are the other 8 guys. So each of these is a set system that is not a delta-matroid. All of its minors are delta-matroids. So these are also excluded minors. And we're going to take all the partial duals of these set systems, which are just related to these guys. And you can characterize all of the delta-matroids. You can characterize all the delta-matroids using these excluded minors. So if I have a set system that doesn't have any of these, it's a minor, then you have a delta-matroid. So you can think of a delta-matroid as always living inside of the Higgs lift between dmin and dmax. And what are you able to remove and keep a delta-matroid? Well, you have to just avoid building any of your excluded minors. Thanks very much.
Are there any questions for Carolyn?
So can you just tell me what geometrically S and T are? So S was, so you're looking at the hypercube, and what are the feasible points? So the origin
No.
is feasible, and then...
So I'm taking the empty set being feasible, and then the full set being feasible, and those are all of your feasible sets. So this is S3. Well, okay, E1, E2, E3.
Yeah. And what was the other one?
And we'll take the other S's. They all.
No, T. You had a T there also.
Yeah. There's.
Oh.
Each one of these has either 3 or 4 elements in its ground set, and they just happen to be the excluded minors. Yeah. So there's 8 guys outside of the infinite family. So it'd be nice if we could just say these are the only 8, but there's that infinite family. But the infinite family is well behaved.